Okay, in this video we're going to look at something called a half-range Fourier series expansion. And the idea is, instead of our normal Fourier series that's defined from minus p to p, we're going to be looking at functions that are defined from 0 to p. So for this example, I'm going to be looking at the function x squared defined from 0 to 2. So just one side of the x-axis, whereas normally we're used to seeing both sides of the x-axis. So there's actually three ways that we could try and turn this into a Fourier series. One is to assume that this is actually an even function and we're only seeing the right side of it. So if the right side of the function was x squared and it was an even function, the left side would also have to be x squared. And so then, given this entire function, x squared from minus 2 to 2, we could find a Fourier series expansion, which, since it's even, would end up being a cosine series expansion. So just multiples of cosine with coefficients. Okay, that should end up giving us this function. So um, a periodic extension of the cosine, the cosine series is going to be a periodic extension of the original shape and its mirror image, which is the uh, even function copy of the original. Okay, so that's one way we can find a Fourier series, is what's called a Fourier cosine series. Another way we can do it is find a sine series. So assume that this is the right half of an odd function. So at first glance, that seems a little strange because our function is x squared. How could that be odd? But if you think about it, what if it was a piecewise function where the right side was x squared and the left side was minus x squared? This is a piecewise function, but it is now an odd function. It has 180-degree rotation symmetry around the origin. And so if I wanted to find a series for this, I would end up finding a sine series. And so it would be a periodic copy of this shape that I have drawn. So it would end up looking something like this. And these vertical lines are vertical asymptotes. Don't worry about those. Um, let's see. Something that's important to note is that since you're finding a sine series, in the previous picture you were finding a cosine series, all of our integrals we actually end up integrating from 0 to p, so we would only actually end up integrating on this chunk anyway, so it doesn't really matter whether we say the left side is x squared or minus x squared. We're still only going to be integrating the right side. So just keep an eye out for words in the problem that say, oh, you're finding a sine series or a cosine series, or oh, you want this to be an even function or an odd function. That's going to tell you which method you should use. Okay, so what if we don't see any of those words? Nothing that tells us to use a sine series or a cosine series. Okay, sometimes it's just called a half-range Fourier series or a Fourier series from 0 to 2. And the way we've been describing Fourier series up to now is we just have periodic copies of whatever shape we have. So if I have periodic copies of 0 to 2 looking like this parabola shape, then I guess we would need another parabola shape from 2 to 4 and another one from 4 to 6, which would actually end up looking like this, more or less. Again, ignore the vertical asymptotes. Okay, so let's think about how we would actually calculate the Fourier series for this. So one option is to say, okay, I'm going to set p equals 2 and integrate from negative 2 to 2. And so then I would actually have to find a piecewise function where one piece is the x squared shape and one piece is whatever this shape is, which is probably y equals x squared shifted to the left. And so then we'd have a piecewise function from negative 2 to 2, and we'd be able to integrate that. It turns out there's a slightly easier way than integrating from negative 2 to 2 and having guaranteed piecewise functions there. And it's this following idea. Um, if I wanted to go from minus 2 to 2 and say, is this double shape copied, that would work. It's probably easier to just think about it as a single shape being copied. So why don't I think about this shape being copied? And if I wanted to do that, I'm going to try and cheat a little bit. So let's look at this shape. So I've moved my gray shape. Instead of going from 0 to 2, it now goes from negative 1 to 1. And if you look at this shaded in shape, which looks kind of like a trapezoid on the left, it's the same size, it's exactly the same shape as this white trapezoid between 1 and 2. So that means the area of this gray shape now is the same as the area of this gray shape now. So moving left and right isn't changing the area, and also multiplying either one of these by sines and cosines, since they're both going to be periodic, should do the same thing. So even though I should be integrating either from -2 to 2 or from -1 to 1, I should be able to finagle it, shift it, and say it's going to be the same integral as integrating from 0 to 2. So that's going to be the weirdest thing. The Fourier series with a half range Fourier series, not sines, not cosines, just the half range Fourier series, is going to have to be a little careful with its powers of 2. Um, Here's what I mean by that. So if I'm really going to be integrating from 0 to 2, then that means that my p is really going from 1 to -1. My p is actually 1. So that's something to be careful about with your Fourier um, series. We're actually going to have p is equal to 1. Um, that's also going to make all of our other formulas have been the same formulas essentially. The Fourier series, the sine series, the cosine series all use the same integrals. This one's going to be a little bit different because we're not doubling and using symmetry. We're actually just going to be using the right hand side 0 to 2, and that's it. So I'm going to post the formulas that you guys need to think about, and just be careful with the 2's is my word of warning.